Well, I have the honor of moderating another panel, and this is a fantastic one. You know, UC Davis has its roots in agriculture. We're often ranked the number one school in agriculture in the country, and sometimes in the world. We go back and forth with Wageningen University, which is based in the Netherlands. I've never visited them, but I do intend to just double check and make sure. But we're really, really thrilled to kind of be able to have this next panel because it's certainly near and dear to UC Davis's heart when it comes to kind of thinking about sustainable food systems. And of course, decarbonization is going to be critical for that. So what we're going to do for this this breakout session is we're going to bring up 4 experts that are going to be able to talk through different perspectives. First, we're going to have Nick Karki come up. He's an energy and environmental researcher at LBNL, and he's part of the UC Davis LBNL team that's really been driving this industrial decarbonization solutions hub. And so he'll provide an overview of kind of thinking about the food and beverage sector and where those opportunities are for decarbonization. Next, we're going to have Ammi, Amarnath, who I've known for quite some time. He's a principal technical executive in electrification and sustainable energy strategy research sector. He may have the longest title that I'm aware of, but he doesn't just spend time in the food sector. He does buildings. He does smart grid edge technologies as well. He's definitely been looking at the energy water nexus for some time. I think since we've been talking about this since we first met Ammi, and he'll be presenting some work that EPRI has been leading on decarbonization opportunities with food warehousing in the warehousing sector. And then Professor Nitin will be coming up shortly thereafter. He's a professor not only in the bio and ag engineering department, but also the food science and technology department. And he'll be talking about food processing opportunities and food processing specifically. DOE, I think, referenced a potential research project that they're funding, and Professor Nitin is partnered with another faculty here at UC Davis on that, so he'll give us an in-depth look at that. And then my fellow namesake, Ben Schlegelmilch from Leprino Foods out of Tracy. He'll be sharing Leprino's experience with one of the few my understanding is one of the few industrial heat pumps that's been deployed in the U.S. And so that'll be a really interesting opportunity for us to hear from him as well. So with that, we're going to invite Nick up to kick us off, and please join me in welcoming him. All right, this microphone's on.
Thank you. All righty. So today I'm going to talk about the decarbonization of the food and beverage sector in US and as well as California. And this kind of stems out from our collaborative work with UC Davis Energy Efficiency Institute. So my name is Nick Karki. I am an energy/environmental researcher at Berkeley Lab. I work with Prakash Rao, who is a research scientist at the lab, and also in terms of UC Davis EEI, we work with Professor Kisak, who is also a faculty scientist at the lab, along with 3 other graduate students, so Ali, Oves, and Vedant, specifically for this project. So to contextualize the US food and beverage sector, the F&B facilities in the US, and looking at how the production is projected, across 2033, right? USDA projects that it's going to be a linear increase in many of the food commodities and products across 2033, and it's going to increase all the way up to 2050 as well. So you can look in the graph below. There are a lot of products that will see all the way up to 20% increase, right, in production. So we're already having to decarbonize whatever it's in front of us in terms of emissions, but there's also it's a lot of hard work that needs to be done in the coming 10 and maybe 20 years across 2050. So there are about 41,000 F&B facilities in the US, and they generate around 8% of US overall industrial emissions. And in the diagram that you can see on the bottom left, it's more than cement, and it's almost equal to iron and steel. So it's an energy as well as emissions intensive sector, that's for sure. It also represents 2% of U.S. economy-wide emissions. So that's a lot. So a bit looking into it, you can see, so this diagram on the bottom right that I just showed, it's from the Manufacturing Energy Consumption Survey, 2018 mix data from US EIA. So what it pretty much tells you is the scope 1 and scope 2 emissions on a national scale is divided or is in a ratio of around 50%, right? So all the way on the left of that chart, you can see it's around 48 million metric ton for purchased electricity related scope 2 emissions, and overall emissions is 96 million metric ton of CO2e, which is on the top right of the chart. And then the remaining emissions, which is the remaining 48, that's really your scope 1 emissions mostly from your stationary combustion within the sector. And that's a lot of emissions. And these are primarily driven by your CHPs, your boilers, your process heating, your HVAC, and all that. So we really need to look into that. That's what we tried to look into this. Going further deeper into this sector, we have different thermal processes within the sector that utilize fossil fuels, right? That's really stemming out the scope 1 emissions. The chart on the x-axis is the temperature of these processes, and then the y-axis is the fossil fuel consumption. And this is also based on 2018 mix data from US EIA. So you can see that a lot of these processes are really, low temperature processes, right? They do require hot water, hot air, or steam. So that is pretty, well spread out for those temperature ranges, but it's not high. So that's one, advantage. The temperature that we really need to be looking at is not high, but the challenge is that there are like hundreds of different processes, right, in the food sector, food and beverage sector, F&B. There's just so much, and one process is not like the other, and that's the thing that we're looking to decarbonize. So from our collaborative work that Prakash and I are doing for industrial efficiency and decarbonization office from DOE on the industrial decarbonization roadmap report, we've identified obviously 3 different decarb pillars. As per DOE, there are 4 decarbonization pillars, but we thought the scope of CCUS for this sector is limited. There might be cases here and there, but it's not really as representative. So obviously there are EE trying to look into equipment level, but not just that, but we also need to be looking at distribution systems, right? Even if you electrify some of your thermal equipment, you're still gonna have the distribution system, and they need to be really efficient. Machine drives, process integration, so you can utilize different heating and then cooling processes and then kind of integrate them with heat exchangers or heat pumps, and that's going to reduce energy consumption. Electrification of process heat, so hot water and steam generated heat pumps, they have a lot of scope. This sector primarily will be driven a lot by electrification. That's why these equipment are really important. And then there's low carbon fuels and energy sources. So generate your own on-site clean electricity, but also biogas. You can get off-site biogas, but you can also utilize your food waste, which is really prevalent within the sector, to get on-site anaerobic digesters originating biogas. And if you have a lot of it, you can upgrade it and then utilize it as RNG or sell it as well. There are additional opportunity in terms of advanced combustion as well as refrigeration. So there are a lot of different decarb solutions for the sector, and this is by no means a comprehensive list, but this was some of the stuff that we looked at. Now, with that being said, all right, we wanted to contextualize the food and beverage sector. It's around 6,300 facility operating in California. These are the 6,300 F&B manufacturing facility, which is around 15% of the total US facilities, and that's a lot. And it's by far the largest. I think the second is Texas, which is around 4,000 facilities. So California is by far the largest. A lot of revenue, a lot of people being employed. And also, a lot of emissions. So it represents greater than 7% of US F&B sector Scope 1 emissions. And this is based on 2022 CARB, mandatory GHG reporting program. So these are only based on the facility that really reported to the program, and they were around 100. So we're still not, including all the thousands of different F&B facilities in here. So they do represent a lot of Scope 1 emissions, as well as Scope 2, obviously. So to look at a prototypical facility that might be operating in California and quantify the decarb solutions and their importance and their carbon abatement potential, we developed a prototypical food facility. Now, this is based on 2018, again, mixed data. And you have your usual high-level processes, right? Your boiler, your process heating, CSPs, and all that. And we utilize a tool, a Sankey tool, which generates this Sankey diagram on the bottom right. So this is a tool that we developed with our collaborative effort between LBNL and UC Davis. It's in industrialdecarb.lbl.gov website. So what it really does is it's basically, generates a carbon flow of your facility. So based on whatever energy your processes or equipment are using, you just plug it out or plug them in and then get this diagram. So that's really the emissions. And as you can see, it's a bit different from the first chart that I showed, in the sense that I mentioned the Scope 1 and Scope 2 emissions is 50-50, right, on a national scale. But if you look at California, it's more like 70-30, because the grid is cleaner in California as compared to national grid emissions factor. So it's a bit different, and we're really looking at Scope 1 emissions. Not to diminish the importance of energy efficiency in your electric equipment, but yeah. So this is basically all the gist of it, the result. We looked at, for the year 2022, we looked at two different scenarios. One, we didn't include energy efficiency, and the second one, we included energy efficiency. So in the first one, what we did was we included just the electrification and low carbon fuels and low carbon fuels. And the second one, we included electrification, low carbon fuels, and energy efficiency. So we did this to highlight the importance of EE in terms of carbon abatement, but also in terms of what's the cost implication look like when you do energy efficiency and when you do not. So the first diagram. So this is another of our tools that again came out through our collaborative effort with UC Davis Energy Efficiency Institute. It's called an LCAC plot generator. So what it really does is it creates this graphs out that has annual carbon abatement on the x-axis, and then carbon abatement cost on the y-axis. So it's LCAC plot, that's levelized cost of abated carbon, or avoided carbon, whatever you want to call it. So what it really does is it contextualizes, or it puts these different measures on a graph, and then kind of lists out what the cost would look like, right, if you want to implement it, and then how much carbon it's going to abate on the x-axis. So what we see here is, for the state of California, I mean, on-site solar, it's really cheap. It's a revenue-generating measure. As you can see, it's lower than zero. So that's a couple of reasons for that. Electricity cost is really high. So if you're generating your own electricity, then it's going to be cost-effective as well. And then the sun hours, right? California, the sun hours is around 5.2 watt per meter square. So that's a lot of good sun throughout the year. So that's one thing. And in terms of cost, I also want to call out the couple of numbers on the top right. So you can see carbon cost in there. So that's the cap and trade related carbon cost in California, which was around $27 per ton. And then the other one is average cost of carbon. So that just means that if you implement all these measures, then it's going to, on an average, it's going to cost you this amount of money per ton of carbon abatement. So heat pumps are also really economical in the sense that what we did here was we also included the cap and cost related measures, right? So cap and cost related advantage or savings that you get when you replace your boilers. So that's why heat pumps are also economical. And then there are RECs, renewable energy credits, purchased in order to get clean electricity. And then remaining one is carbon capture / offsite biomass / electric boilers. So we kind of group them all because they are really expensive, and we really think that heat pumps are way more efficient than putting in electric boilers. So that's, and the overall annualized expenditure for this this scenario is around $230,000 or $240,000 per year. So it's going to cost you money to emit the carbon in that year. Now the second chart that we have is we also included energy efficiency. So we pooled all the energy efficiency measures related to your thermal processes as well as other machine drives. And then we also have process integration. So if you just look at the annualized expenditure at first, I mean, there's a stark difference, right? There's just so much of a difference between scenario 1 and scenario 2 in terms of annualized expenditure and the average cost. So average cost comes around $3 per ton. It's visible, yeah. Minus $3 per ton, which is really different as compared to the $50 per ton of carbon cost abatement. So that's the thing. If you do these, I mean, if facilities find it cost effective to perform these measures, right, the on-site solar, the energy efficiency, the heat pumps, that are lower than the cost of carbon in the state, then, I mean, that's one way to start doing it. And EE, they have to be done either ahead of time or simultaneously with other measures. Otherwise, everything's gonna be way more cost prohibitive, and nobody wants that, right? So finally, with all the opportunities that I lined out here, I wanna end up with some of the barriers because, I mean, nobody wants to put in a high temperature heat pump as the first person, right? I don't wanna install it as the first person and then maybe lose money on that. People just wanna look at it and then, oh, people are doing it, then they wanna start it. In this sector, there's this issue related to food and safety compliance and whatever customer perception it is, right? People want to have the stuff that they have always gotten it, right? They're the conventional stuff, they don't want change. And a really important stuff is high CAPEX and OPEX in terms of these decarb measures. So this high CAPEX, it's normal, but in electrification, because electricity is so expensive, it really is cost prohibitive. So even if you have a heat pump of COP like 4 or 5, there are some cases where you're gonna have to, your annual expenditure in terms of electricity is gonna be way more than, way more than what you're already paying. So there are issues like negative payback. So if you don't have savings, you don't have a payback. So what do you do, right? So there are these cases that really need to be handled. But there are far more opportunities as well for the sector in terms of decarbonization. So with that, I want to end my presentation. Ben, are we taking questions now, or?
Let's go. Let's actually take a moment for 1 or 2 questions.
Okay.
So we have a roving mic, and I will leave the mic to the rover. Any questions? Yes, Steve.
Well, I don't know if it's a quick question, but when you were showing the cost of carbon and solar was highly negative cost of carbon and heat pumps were slightly negative cost of carbon, and you said something about heat pumps being economically viable, but they're not because of the spark spread. I just didn't understand that. Can you talk a little more about how heat pumps ended up as a negative cost of carbon?
So 2 different major things. So one thing was, for that analysis, we assumed all the electricity that the heat pumps or any other electrical equipment are going to use are going to be totally clean. That's why we included on-site solar-related electricity and also RECs on there, renewable energy credits. So that's one thing. And the other thing was we also included the cap and trade-related costs in there, so $27 per ton, which kind of brings things out, which really reduces the cost. So due to these two reasons, the cost of heat pumps came out. I think it was around -10. So primarily that.
All right, let's give Nick a big round of applause. Thank you, Nick. All right, Ammi, stage is yours.
Assume the slides are loaded. Yeah, thank you. Good morning, folks. Ammi Amarnath from, oops. Maybe I shouldn't hold it. Oh, no. Yeah. Can you hear me okay? Yeah, okay. Ammi Amarnath from EPRI, the Electric Power Research Institute. I don't have a slide about EPRI, but I'll just talk about who we are. We are the Electric Power Research Institute, a public-facing R&D organization, national and global. We are mainly funded by utility companies around the country. Say we have about 90% of all utility companies in the US funding us, and about 35% of all utilities around the world funding us. So it's probably one of the largest R&D groups in the public-facing utility sector as such. Public-facing means we do our research all for the value of the customers, not really for the shareholders of the utilities as such. So today I'm going to talk. I've been asked to talk about industrial refrigerated warehouse, which is slightly different from the Scope 1 emissions, because as you know, industrial warehouses are electrically driven. They've got compressors and so on and so forth. So it's really all about Scope 2 emissions in terms of, how can efficiency be gained by using electricity more efficiently, and also be able to, shift the load. I'm going to talk about a little bit on the shifting of the load that's used in the warehouses. As a background, I should also mention that I did a lot of work with UC Davis in the 1990s with the Food and Agricultural Department here, with Dr. Sharon Shoemaker, who probably has retired by now, but with her we did many projects. One big one being membrane technology and demonstrating membrane technology for water and wastewater treatment for the food processing plants around California. So a lot of history with UC Davis, Ben. Wonderful history, yes, indeed. So, demand flexibility. I'm going to talk a little bit on this particular subject for the refrigerated food warehouses. Okay, what is demand flexibility? Demand flexibility is now what some people call as demand response 2.0, or flexible demand response. Initially when we had this demand response requirement here in California and other parts of the country, it was really to just lower the loads or lower the power that's used by facilities, the industrial facilities, food processing facilities, and so on and so forth. But really now, at some periods of times you want to use more electricity, because if you have more renewables, which is all variable and flexible, you want to use more of that product. So that's really what the flexibility is all about. It's both up and down. So how can we do demand flexibility in refrigerated warehouses in California? California, as you know, is really big in food processing. We heard this earlier on, and consequently, the food has to be moved around. So it's very big in refrigerated warehouses, because we need to store the food products at some middle point before it's delivered to the grocery stores and to your homes, your and my home, for consumption. So there's a lot of power that these warehouses use, for storing refrigerated foods, and the idea is how can we make them more flexible, more efficient, and so on and so forth. Okay. These are all the services that are offered by these large refrigerated warehouses here in the state of California. But the biggest ones are these freezer rooms. Food is stored at, mainly around 0 degree Fahrenheit, but ice creams and all need to be stored at a much lower temperature, as some of you may know. So So there are things, but they do use things like blast freezers. This is very interesting in the sense that if you want to freeze, chicken as it's being processed, you do the blast freezing so that you kind of freeze it immediately. More of the skin is being frozen so you can use it as fresh food later on and things of that nature. So it's a very interesting business, in this thing. So what we did was we were very fortunate to be awarded from the California Energy Commission a grant to look at this sector and to see, can you achieve 20% demand flexibility both up and down? Okay, can you do that? And one way to do that is to be able to use some of the newest communication protocols, especially OpenADR 2.0b, to send signals to the controllers in the food warehouses so that the power can be increased and power can be decreased as such. So this is really what the project was. So we worked with one of the largest warehouses in the country. Lineage is probably one of the largest in the country and probably one of the largest in the world. And they've got many warehouses here in California and around the country. We worked with one in Mira Loma. Mira Loma is very close to Riverside, if you know that area. Pretty hot place, but huge warehouses there, including Amazon warehouses and so on and so forth. So this is a very large warehouse that we did our experiments in with. They've got a 4 megawatt load, for the plant as such. So over $1 million of consumption of electricity every year. So first thing we need to do is we need to understand what the plant loads are, like how energy is being used in this load. So on the left side, you see, where the average load is, for the whole plant in terms of, throughout the day. It's pretty even because it's a 24/7, operating plant. But the right side is even more interesting, and that is, the compressors that are used to freeze the food. I mean, the refrigeration systems. We think that's the most important. But look here, there are other plant loads also in there that are useful, and I'll talk about it a little bit as we move forward. So what we did was, we used the OpenADR 2.0 communication architecture, if you know what I mean. By sending signals from our own server, and because this is a test, so we couldn't use the demand response automation server from any of the utilities. So Southern Cal Edison is the utility there. We couldn't use it from that because it's an operating plant and it's an experiment. So we have our own DRAS or VTN, virtual terminal node, where we can send signals, OpenADR 2.0 signals. So we sent those signals. Those signals were grabbed in the cloud, and the signals were sent to the plant. And we configured the plant, or we worked with the company that configures the operation of the plant so that the plant can use electricity more appropriately. In other words, can it turn off some compressors? Can it turn on some compressors? Can it overfreeze the food? Things of that nature, okay? But what's interesting that we found was that, the set of compressors they have in the plant, they're all interlinked. So you kind of, increase the power usage in one room, one refrigerator room, it kind of affects the other rooms, okay? So you've got to be very careful. You've got to do it very finely tuned. So it's really a warehouse by warehouse application is what we need to do. So we were able to send signals. That's the most important part. We were able to send signals, but to control it up and down was rather difficult, okay? What is most interesting in these warehouses, think of a warehouse as a thermal battery, okay? If you compare it with a battery, it's sort of in the discharged state. In other words, it's kept at a very tight temperature, each one of these rooms, so that you cannot just, let it float or increase the temperature because it will spoil the food. So what one has to do is, you got to kind of, make the rooms use more power. In other words, power up first, and then you can power down. Okay, so if you have like a emergency signal on next day, you're going to have a problem on the grid and all, today is the time to power up, to be able to use more energy and to store the thermal mass. So it's a very clever way of operating, and we did that. And what we found was we were able to power up and power down by more than 30%. Actually, power up by about 26% and power down by about 30%. So we were able to do that only for the compressors. Okay, remember compressors are only half the plant load, and so we were able to do this. I'll just skip to the next slide. So I told you that there's a lot of other power that's used in the warehouses. So there are floor heaters. Okay, so every food warehouse has to have floor heater because you can't. If there's a thermal gradient between the frozen room and the ground underneath it, the ground will buckle, and your forklift trucks can't go on top of that. So the floor has to be heated. These are all heated by some sort of an electrical method. In this plant, it has 700 kilowatts of electrical resistance heaters that you can just power up. You can just turn on and turn off. You can connect that. We didn't know going in, otherwise we would have connected that also. And the second thing is that they use a lot of electric forklift trucks. Okay, obviously these trucks are the ones that move the food in and out. So it's a lot of power that's used there. And you can do demand response or demand flexibility on those also. You can charge at appropriate times. There's a lot of research going on charging vehicles such that. So we learned a lot from this. Open ADR can be used. We can do demand flexibility in such warehouses. But what is most important is you got to understand the plant. You got to understand exactly how the plant operates. Only then we can do that. I just want to give some acknowledgements on this particular project. A report has been published by the CEC. Karen Perrin from the Energy Commission, she supported us a lot. And Mark Martinez and other people from Southern Cal Edison and the other people that you see here supported me on this particular very interesting project. I just want to kind of, this is the very last slide. I just want to kind of, shift forward and say, this morning we heard Commissioner Baker talk about, one of the things we need to do is to have low cost of electricity. We need to see how we can control the cost. So one of the initiatives that is going on here in California, by the way, which has been very successful in Denmark, in Norway, and in Spain, is what is called as dynamic pricing. The price of electricity at the point of use, okay? What is the actual price? So the California Public Utility Commission has put out a framework called the CalFuse framework, where the whole idea is to push these dynamic prices to the end-use customers, okay? And the way the thought process is going, there are pilots that they're ongoing right now. For example, we are supporting Southern Cal Edison in one of those pilots, is to first develop a price machine, a machine that actually calculates the price, and to store that price as a signal in a server. And that, CEC has developed the Midas server, that is where one could be stored. And then aggregators or automation service providers can pull those prices and be able to do some interesting thing with the customer. For this food processing plant, for example, if the prices were dynamic, then the automation service provider or maybe even the plant could pull these prices and do some tricks and turning up the temperature up or down or whatever it is. So this is a very interesting opportunity for food processors to take advantage of flexible prices as they come up. So with that, I conclude my presentation, and I don't know if we have any time for questions.
Maybe one question, and then we'll kind of go ahead and switch to Professor Nitin. Yes.
Hi. My assumption is that the dynamic pricing is only the kilowatt hour charge and not the distribution costs, and the distribution dominates. So is there any thought about having the distribution also be based on congestion?
Good question. Yeah, it does include everything. It includes the distribution cost, it includes the congestion cost, it includes the transmission cost at the node. Also, you can put in the greenhouse gas prices if you're able to provide that too. So it includes everything. It's a very comprehensive set that has been developed by the CPUC.
All right, let's give a round of applause.
Thank you.
Good morning, everybody. Can you guys hear me well? Thank you again for the opportunity to talk about today. So I'm going to take a little bit deeper dive into food processing. Nick and Ammi introduce the topic of food industries, I'm going to take a little bit deeper dive into what happens in the food industry itself and how there are opportunities to save energy and contribute to decarbonizing goals in the industry. So I'm particularly going to talk about food-grade materials as catalyst, which can enable decarbonization in the food industry. So we're thinking about, can we use food itself to enable decarbonization in the food industry, particularly from the food processing perspective. So before I start, I'd like to acknowledge the contributions of some of the key members of my lab who have contributed to this research, and also want to highlight our collaboration with Professor Vinod Narayanan. He has been the inspiration behind some of our efforts in getting interested in decarbonization space, and also some of the funding and a pending award from DOE that is still under negotiations in this area. So when we think about food industry, we use significant amount of energy and water. And this is what core of food processing look like. So you get a raw material, it needs to be cleaned, washed extensively with water. Sometimes we use hot water to wash it. And then after we're done, then the next step comes processing. And most of the processing till date in food industry use thermal heat, often using steam or hot water in different forms. And then after we're done processing, we have to clean it. And cleaning still requires, again, hot water or steam, depending on what operation you're running in. So heat in different forms is being used, and most of the heat is lost in the operation. We cannot recover the value of that heat as it is being used in the industrial operation. And I'll go into why that happens. And in terms of the emissions, significant amount of energy comes from natural gas in food processing environments till date. Now, I'm going to talk about a process called CIP. It stands for clean in place. Essentially means that you don't have to dismantle the food equipment. You are going to clean it as it is. So imagine that you are in a kitchen and you got a complicated machine that you need to clean it. How would you clean it without dismantling it? So what you do is you profusely wash with hot water at very large amount of water volume, and water volume in the range of 80 to 90 degrees centigrade, and this is recommended because you don't want cross-contamination from microbes that may have built into that unit while you're processing the food in the previous shift. So that is required for the safety of it. Now this gets extreme when we look at certain industries where they're thinking of using steam instead of hot water. And again, this is mainly driven by industries where we cannot use water to clean it itself. So there are a range of industries, tree nut industries, where we don't introduce water at all because they're dry environments. So use superheated steam in those cases so that you prevent condensation of water, but then again, you're increasing the amount of heat that is being used in a cleaning operation in those cases. And the goal is still to inactivate microbes in both these processes. And if you look at some of the common industries that are very well grounded in California system, dairy industry and the fruit juice industry, these are some of the estimates of the energy use, and they're huge in terms of the teraBTUs amounts. But also if you look at, we spend this much energy in processing food and this much in cleaning. So we are spending about 30% of the energy in cleaning as what we're using in processing in each of these operations. And then sometimes we get an issue with the food safety. And for example, you have a recall in a commodity like cantaloupe. I don't know how many of you follow food industry, but often there are recalls in food industry because of food safety challenges. And for example, this is a news from 2023, where we had a cantaloupe recall in 19 states. And then as a reaction to that, food industry decides, well, what we need to do is we need to actually process these fruit, which is a minimally processed quantity, start thinking about treating with heat. And if you do a brief calculation that even if 10% of those cantaloupes, which are sold, about 70 million cantaloupes in the country, which we really love cantaloupes, by the way, in the nation, they've come in all forms of melon, we would be using significant amount of energy and contributing to significant carbon dioxide. So these events takes place in the industry, and that changes the entire dynamics of how we think about food itself. So I just want to highlight some of those aspects there. And again, the goal is to inactivate microbes. So large amount of energy in food industry is being driven with the motivation to inactivate microbes. And so that made us think about the next concept of catalyst. Chemical industry has been using significant work on catalyst area where we use catalyst predominantly to lower the energy barrier. So things that don't happen at certain temperature, we can introduce a concept of catalyst that lowers the energy barrier and makes the project lot more efficient. We thought, okay, how can we do this with food grade materials? Can we do this with simple materials that may interact with microbes? As I said, microbes are the target, that may interact with the cell wall or the membrane, or may interact with the intracellular components of microbes, but these compounds by themselves are food grade, so they are not antimicrobial. But maybe then when combined with other energy sources, they become activated and can lower the energy barrier. So if a food processing process takes place at 90 or 100 degrees centigrade, maybe we can lower it down to maybe even 55 degrees centigrade. And if we can lower it large enough, then we can start thinking about even using waste heat. The heat that is coming from spent sources, then we can start thinking about using that heat in the process rather than using active heat from more fossil fuel burning. So we investigated this concept. This is a food grade antioxidant which is made by taking a phenolic acid, which occurs in all your fruit. So if you eat your fruit, you're eating gallic acid. It's modified in this case by a small tail. We did another modification in the lab where we took a vitamin C derivative mixed with a lauric acid. This is actually in your milk. And we combined it to make another molecule. And the reason we are doing this is to enhance their penetration into membranes of the cells. So that's why we're doing it. And these are food grade modifications. So when you eat this product, this actually breaks down in your stomach, releases the fatty acid and the vitamin C derivative separately. The same thing happens here. Release the carbon tail, which is a short alcohol molecule, with the phenolic acid separate during your digestion. So we looked at this process of looking at, can we then do pasteurization, for example, of an apple juice at much, much lower temperature than what would you typically do it at? So we introduced into a room temperature this molecule called propyl gallate, which is a commercial antioxidant. At different concentrations in different juices, you don't see any inactivation. So compound by itself does not do anything. But when we combine with a mild heat, by the way, heat also doesn't do anything. This is a sample without PG, which is heated in a gray bar. So heat at 55 degrees centigrade doesn't kill microbes, by the way. That's why we need much higher temperatures to kill it. But when this compound is present in combination with these heat, it actually achieves significant inactivation. Now, this is not a linear scale. This is on a log scale. So that means that we are achieving 5 log reduction, which is 99.999% reduction, which is required for pasteurization in this case. So illustrating an example of food grade compound and a low heat, creating a synergistic combination that leads to inactivation of microbes, lower the energy barrier, and potentially lower the carbon footprint of the processing industry. Not only that, it reduces the fouling. Actually, the reason we use so much water to clean in the first place is because we use high temperatures. When we use high temperatures, food materials tend to deposit on the surfaces. You all have done cooking, so when you boil milk in your pan, if you boil milk for long enough time, you'll get significant fouling on your milk container, and it's hard to clean, by the way. So you have to use a lot of water and heat to get rid of it. So if you can do this at a lower temperature, you reduce fouling, and maybe you reduce the amount of water and energy you need to clean it. So similarly, we did work with the milk powder. Spray drying is a process that is quite energy efficient, but it's not a pasteurization process. So we were trying to understand if we can actually combine spray drying with one of the antioxidant compound that we modified in a lab to actually achieve a pasteurization level in a spray drying process. So clearly, the compound by itself, again, as I showed, does not have an impact. The spray drying does not kill microbes. So if you dry powder, doesn't make it safe. By the way, we know because that we had an infant formula crisis in the country where powder got contaminated and we couldn't get rid of it. So here, the compound and the spray drying process actually achieve significant level of inactivation. We have done this similar process for the decontamination of fresh produce. This was motivated by the cantaloupe issue, that can we actually achieve significant level of inactivation by combining a biocatalyst and a mild heat in this case. Now, the other topic that we have been inspired by is that not only we use energy in making food, we actually waste a lot of food. And by some estimate, in terms of carbon emission, that is the bigger culprit than the entire food processing industry combined. Okay, so not only we make food, actually we waste a lot of food. By some estimates, this is the amount of food waste is equivalent to running 42 coal-fired power plants. And this is in the US with one of the best food infrastructure in the country, in the world. Now, if you think across the world, this is much, much larger contributions because many countries don't have refrigeration, don't have the supply chain. This food waste issue can be such a big issue across the globe that we could be we're significantly contributing to carbonization beyond the energy use in this case. So we were thinking about a solution. Again, my lab does a lot of materials work, so by now we are inspired by materials and their catalytic properties. We were thinking of a process where we could use the food waste or food byproduct to actually make something useful out of it. This work was done in collaboration with Selena Wang, who works on olives. She works on olive oil. So we took this collaboration. We said, okay, we were isolating those phenolic compounds. Those are very rich in these pumice samples that are left behind after you extract an oil. So we developed a process of extracting some phenolic compounds from it. So without any modification, we said, okay, let's look at their potential to create some antimicrobial scenarios. And we found that these compounds, when they are present together in this pool, are highly synergistic as compared to individual compounds. So that gave us a significant insight into how these compounds may be used. And I'll illustrate an example of it. So this is in a project we did with an industry, so I won't share the name of the compound, of the fruit that we were working in this case. But this is a fruit that is a very high value fruit and has a shelf life of 14 days. Okay, so the industry came to us saying, can we actually extend this shelf life, but we don't want to impact the fruit at all. Okay, so we can't introduce anything that is modified in this fruit. So everything has to be a food grade. So we looked at it. We introduced our combination, which we call it OPE, which is olive pomace extract. And this is what happens to the microbial load if without that olive pomace extract. What you find is that by day 14, you exceed the threshold levels where you start getting fermentation smells in this food. And likely as a consumer, you throw the food away. So if we wash the same fruit with this extract with a mild heat at 60 degrees centigrade, you actually can prevent this fruit from getting spoiled even at 21 days of time period. So we have extended by 7 days the shelf life of it. Likely you'll consume by that time. And hopefully we can reduce the food waste problem. So we're looking at this issue of how to develop coatings, how to develop materials that contribute to food waste, but also thinking about how to do decontamination while we're processing the fruit itself. So as you discover these materials, one of the role in university is also to develop some fundamental understanding of these things, how they are working. We've been looking at some machine learning application where we're looking at can we predict what these extracts and compounds are going to have functions. We are using some machine learning tools. And in the interest of time, I'll be brief. We are also using some NMR-based metabolomics to understand how these compounds actually interact with microbes and eventually gives us the function that we required, with the hope that we can optimize this and achieve desired results of optimal combinations. Again, this is similar to what catalytic chemistry lab will do in a chemical industry. So with that, I'll stop here and we'll be happy to take any questions.
And thank you. Thank you, Professor Nitin. I'm going to ask if you're willing to answer those questions at the break and in the hallway, just because I lost track of time here. So thank you. And so Ben, you'll come up and give our last talk. Thank you so much.
All right, hello, I'm Ben Schlegelmilch. I work for Leprino Foods. I've been there about 17 years. I'm a mechanical engineer. So Leprino Foods, we have somewhat a global responsibility journey that we're working on towards 2050 to decrease everything we see in every plant, and we're even building a current plant where we're taking that into account to make sure that we hit our goals. So we aim to lead responsibility. So we look at probably about a 10% reduction every 10 years. It's a big priority for us. And it goes into one of our big company goals and what we want to be. So we installed the ammonia heat pump last summer in July, and we looked at basic concept of where do we get the heat from for it, and where do we put the heat in? So we're a producer of mozzarella cheese. So we're taking milk, and my plant takes 3 million pounds of milk a day, and we're making 500,000 pounds of cheese with it. So we have a milk pasteurizer that we're using a lot of steam in. And we have a big ammonia refrigeration system where we use to cool our product, and we have a big storage freezer in our facility as well. So we looked at the high side of ammonia refrigeration system from our towers, taking that heat that's just wasted, putting that into a heat pump, and then the heat pump is then making it warmer and pushing it towards a reduction in steam where we heat a glycol loop. That glycol loop is repurposing hot water that's heated by steam that is then for a milk pasteurizer. So we looked at a few business cases, how much are we going to save, what are we going to do when it comes around to it, and then we come up with a final process, as you can see here, to implement to our system. And we had to do a little bit of construction in our rooms to make it fit. We had to move stuff around, some old compressors that didn't work, tried to just make it fit. There's 2 components to the setup. Here, our P&ID for the process for both sides. And here's our compressor. So this is one component, is the ammonia compressor. That's then taken the high side ammonia, and we're going from basically, we run our system 160 PSI, sometimes 180, but it's boosting it to, we run about 290, 300 PSI. And then that goes to our condenser skids. That condenser skid is then taking in that now 300 PSI ammonia on one part of a heat exchanger. The other part of the heat exchanger is glycol that we're heating to 125 degrees. And then that's going out to our system. So here's a little kind of what we have for our compressor setup. It tells us everything that's going on in our compressor, how it works, what's going on, functions, what we can control. And here's basically the main control loop of the system. So we have one loop that's sending it to our milk HTSD and our control on how it works. And then we do actually at night when our milk HTSD doesn't run, so every day we do about 4 or 5 hours of cleanup. During that time, our milk HTSD is not running. So we then run this heat pump for the hot water that we're using in hoses to clean our clean in place processes for the facility. So we have a tank, and basically we're supplementing the steam that's going to that tank because that water we want about 140 degrees, and that's then at night. So the system can run 24/7, and we just balance out the loads that it's going to take and how it's going to manage it. And that's pretty much it.
Ben, if you'd stay up there just because there may be some questions. We still have about 3 minutes left, and I think you zipped through a lot of those slides. There may be some questions for you. And then also, Professor Nitin, if there's questions for you, we can answer those too in this last 3 minutes. So any questions for Ben? Yes.
Thanks for the presentation. So you showed the estimated paybacks for the 2 projects was one 7 years, the other 15 years, if I'm not mistaken. So how long have those been implemented, and how do the savings look like so far since the implementation?
Yeah, so we've had it running for about 9 months. And during winter, it's about a 7% savings for the facility, and during summer, it's closer to about 14%. So it's gonna be probably more about a 5 or 6 year payback for the project. So much better. Overall cost was about $2.5 million, but we're saving pretty significant by keeping one of our 3 boilers completely offline.
Thank you.
Just wondering what main barriers you had to implementing this project.
So you're tying into a refrigeration system. You have to deal with government regulations when it comes to that and all the documentation around PSM and refrigeration. That was probably the hardest part of doing that. We at least had opportunities where it wasn't hard to tie it into our system. It was just all the paperwork and everything else that goes with it to make it right and make it work. You're dealing with high pressure ammonia. You have to make sure the system works safely.
Thank you, Ben. All right, let's give all 4 of our panelists a big